So let's revisit this climate sensitivity, which you have already talked about a couple of times, and add the modeling angle to it. But before I go to it, I wanted to also say a bit more about the climate sensitivity issue we are worried about for the future, and what are the various things that go into projecting. They are so complicated that there are many unknowns, uncertainties into the future, but it just comes down to estimating the risk of climate change for the future and what we want to do about it, right? This is the entire debate, as you know by now. So let's put climate sensitivity in that context a little bit. This figure we already looked at from IPCC, where climate sensitivity is basically starting from a baseline and increasing the CO2, global mean CO2, reaching double the amount. So the time of doubling, let's say you're using 1% per year increase, so that's 70 years for doubling, and with a simple model you get the warming to reach this level and stay stable once the CO2 has been stabilized at double the CO2 of the baseline. And then the real model, GFDL, full sophisticated Earth system model, shows that you have committed warming, where even after you stopped increasing CO2, the system keeps adjusting to the CO2 that was put in, so you keep warming, and eventually you will reach the equilibrium that is shown by this simple model, and that's same for quadruple CO2, as we mentioned before. And we are worried about this because we are projecting warming into the future with various scenarios of greenhouse gas increases, not just CO2. So that's another thing to consider. By definition, we are calling climate sensitivity as the equilibrium temperature you would eventually reach after doubling the CO2. So there is a transient response. So basically to the 21st century will be in the transient mode, and the equilibration of the system will take many centuries. Plus you have to convert all the greenhouse gases excuse me, into CO2 equivalent eventually to do that. But the future projections also include very complicated scenarios that are developed with great care. So we are worrying about the mitigation scenarios here, no additional climate policy reference scenario, and this is the emission business as usual scenario. I'll come to that in a minute. And then you are increasing the policy influence on mitigation and bringing down the total radiative forcing. Remember that RCP 2.6 to 8.5 are the net radiative forcing resulting from those simulation scenarios, those future scenarios that were assumed in CMIP 5, and CMIP 6 has gone into these more sophisticated SSP 1 .2.6, SSP 1-2.6, and so on and so forth. So 5 main SSP scenarios are investigated in Working Group 1 under the IPCC. SSP X-Y is additional SSP scenarios, and RCP-Ys are the CMIP 5 scenarios. So indicators of warming, approximate radiative forcing at year 2100 in watts per meter squared, go from 1.9 to 8.5. RCP CMIP 5 had only down to 2.6, but there's been debate about whether 2 degrees C is safe enough as a global warming target for 2100. So 1.1 has been added, and you have shared socioeconomic pathways on top that go from sustainability, middle of the road, regional rivalry, inequality, and fossil fueled development. There are lots of details in what they mean, so you can go and look those up, but for our purpose we will just focus on these. So sustainability and emission scenarios are combined, for example, to create some additional scenario simulations of SSP 1-1.9, SSP 1-2.6, SSP 2-4.5, 3-7, 5-8.5, and so on and so forth. So there is evidence, or there is model evaluation that suggests that the uncertainties in the projections in the first decade or two come from all the modeling issues that we have talked about. As you go into the future to 2080 to 2100, for example, or even 2060 and beyond, the uncertainties tend to be much more about the scenarios. So climate sensitivity has to keep that in mind, and also remember that climate sensitivity is for global mean temperature change for double CO2, whereas the distribution of temperature trends is very critical. So we are looking here at trends for 1900 to 1980. Wherever there are X's, the trends are not statistically significant. So there are regions where there are statistically significant trends, and the main message here is that after 1980, if you look at 1981 to 2020, the warming is remarkably accelerated, especially with the polar amplification, and it is statistically significant. And this is from models and observations. This is where the data do not give us enough confidence in estimating the trends, and this is a critical pace that you should read up when it comes to things like global warming pause and so on. So we are accelerating the warming just like we are accelerating the emissions. So in the context of climate sensitivity, we are averaging all these and looking for that global mean warming number. And the other thing to remember is that if we look at the impact of humans, so this is showing temperatures have increased faster over land than oceans. So this is showing land and ocean trends with respect to this base period. The base period here is somewhat is the same. And annual and decadal averages from data from different data show that they are remarkably in agreement, and even though there is debate about whether there was a flattening of the warming after 1998 for about a decade or so and so on, what is clear is that each decade is warmer than the previous decade. So we have to always deal with these ideas that as a global mean, we are warming, no doubt at all. Land is warming faster than the oceans, which is expected because land has a lower heat content, heat capacity, sorry. And each decade is warmer than the previous decade, even though interannual variability always produces ups and downs, and presumably even some slowing down of the warming rates. And you also have to worry about the forcings that go into these things. It's not just CO2. Even though climate sensitivity is clubbed into CO2 doubling, it gives us a sense of how radiative forcing altogether will determine the climate sensitivity. So climate sensitivity remains a very hairy issue still. So this is just showing CO2 forcing, so in watts per meter squared with respect to some baseline again. Methane, nitrous oxide, ozone, halogenated gases, so those are the greenhouse gases. Tropospheric aerosols have had a cooling effect over this period, but you can see the range of uncertainty is very large. Direct and indirect effects are not. Direct effect can be more easily estimated than indirect effect. Other anthropogenic effects like land use change, volcanic eruptions provide pulses of forcing and can be and are very important. Solar forcing is very tiny, as you can see, and the total, which is shown in the black line here. This is the rate of change of anthropogenic effective radiative forcing, and you can see that we are now per decade into more than half a watt per meter squared of effective anthropogenic radiative forcing. So it's not just CO2 doubling that we have to worry about when we do future projections in terms of climate sensitivity. So in terms of attribution, we have already asked this question: how do we know humans are causing climate change? So we have used the models to separate the contributions for different forcings. So greenhouse gases, combined human and natural causes here, natural causes in the model. We can do that. We can take out volcanic forcings, aerosol forcings, greenhouse gas forcings, and so on. And again, aerosols are cooling, but you can see the range is quite large. Natural causes range is much smaller, and greenhouse gases is larger, and so on and so forth. So this is also clear that we are having an impact. So the question is, into the future, what are we going to do? So eventually we come to this. AR6 narrows the range of for equilibrium climate sensitivity and rules out the low values, which means that if you look at the equilibrium warming with double CO2 from the new generation of models, the CMIP6 models, you can see that the estimate by the Charney committee in the 1970s, which did it without all these heavy modelings and scenarios, estimated the range to be somewhere in the 1.5 to 4.5 range. And the range is not that much reduced if you look at the current scenarios. Okay, why is that? Because we have increased the sophistication of the models, observations have increased, we know much more about the uncertainty. So we are now much more certain about the uncertainties in the climate sensitivity calculations, like the aerosol forcing and the greenhouse gas forcing, for example. So the main message is that the estimates of climate sensitivity have changed, and they have improved in terms of quantifying the uncertainties, but it still remains a very critical and challenging issue for modeling, which means it is a very big challenge for projections as well. So coming to climate models, maybe let me just wrap it up. Looking at our energy balance model, we had solar, which can depend on temperature because of the albedo dependence on temperature, like snow melt, vegetation changes, and so on. This is the black body radiation, which is obviously a function of temperature, sigma T to the fourth. Now we are adding a feedback term which includes water vapor, for example, can include clouds, can include the critical ice albedo feedback. So in the models, we have to get away from just the pure energy balance model we did, balancing the short wave and long wave, but we have to add the feedbacks for climate sensitivity, and of course we have the perturbation due to, let's say, human activities or natural forcing. We can then write these again in terms of the Taylor series kind of idea we had. So A plus A prime, which is the dA dt, the dependence of solar net solar kept in the system with respect to temperature, and times T minus T bar, where T bar is the long-term average and T is the perturbation we are causing. Similarly, other perturbations in black body radiation and how outgoing long wave changes, and how the feedbacks change the energy balance, internal feedbacks, right, that we just mentioned, plus the perturbation. So this is the equilibrium, so that is 0. That's the energy balance we have done. This is the remaining feedback, so A prime plus B prime plus W prime times T minus T bar plus delta Q. So now we can write a feedback term, lambda, net feedback, as short wave feedback, long wave feedback, and other internal feedbacks, which we wrote as A prime, P prime, and W prime. Okay, so here you can write the temperature warming that you will get as the climate sensitivity to be long-term average minus 1 over lambda times delta Q, which is the radiative forcing. So you can write 1 over lambda as S, so S equals minus 1 over lambda plus, so that lets us write this as T bar plus S times delta Q. Why do we do that? Because this can be considered as a sensitivity. What is the climate sensitivity to radiative forcing? This is what we are trying to estimate, right? So write lambda as lambda A plus lambda P plus lambda B plus lambda W, as we said, which makes 1 over S to be 1 over S sensitivity to short wave, sensitivity to long wave, and sensitivity to internal feedbacks. This puts us in the framework of climate modeling and seeking climate sensitivity with all the feedbacks that are in the system. Okay, so just to conclude, we look again at our equations, two-layer equation we had done, where we were emitting from the surface with a gray body, so emissivity of epsilon, and we had that being taken up by the cloudy part of the atmosphere, which we had considered complete black body, so cloud fraction was C, and we had derived solutions for surface temperature and the atmospheric temperature, which was emitting to space, with of course some escaping from the surface, because the atmosphere is absorbing only in the cloud cover, and the surface radiation is escaping to space through the non-cloudy part or the clear part. So we wrote that as a balance of, now we can write that as a balance of short wave, long wave, and the internal feedbacks, where we have left the cloudiness in here, the cloudy fraction in here. So the analogy is that the short wave feedback is basically this term, if we do d alpha dt, because albedo is temperature dependent. A long wave feedback is basically minus 4 epsilon times sigma t to the cube, which is basically derivative of this, so we're taking derivatives of each term. And the internal feedbacks giving us climate sensitivity is the derivative of this, where we are making the cloud fraction also a function of temperature, which is obvious because temperatures are non-linearly related through Clausius-Clapeyron to humidity, and humidity is related to cloudiness, and so on. So we have managed to derive the climate sensitivity now for our energy balance model. Assuming that the albedo is not temperature dependent and the effect of high clouds is irrelevant and no additional forcing exists, we can simplify the feedbacks to get long wave feedback by plugging in the numbers here, to be minus 3.33 watts per meter square per Kelvin. So this is a direct estimate of knowing the temperature change over the 20th century, let's say. This is obvious, right? The long wave feedback is an inbuilt negative feedback. If you warm the atmosphere, sigma t to the fourth to space is going to go up. The height at which it's emitted changes and so on, but essentially that is a feedback. The question is the time scale at which it works. We are increasing greenhouse gases at such a rapid rate that the long wave increase doesn't cool fast enough, so the green global warming happens. Climate models estimate the same feedback, which is also referred to as the Planck feedback, sigma t to the fourth, at minus 3.21 plus minus 0.04 watts per meter square per Kelvin. So you can say models are doing a good job, and remember, models also have to do all this part. So obviously the difference can be related to these things or the model deficiency as a whole. Okay, so this is a bit longish podcast, but that's okay. The concept of climate sensitivity is very critical, and trying to see what is involved in estimating that from the model, especially for the future with all the scenarios and so on, is very important. So I let it be a little bit longer. So now we will go forward and look at ice albedo feedback as an example of the internal feedback that will affect climate sensitivity critically. Okay, we have kind of already discussed this a little bit in the context of the long time series from Vostok Ice Core, saying warming phase goes very fast and cooling phase goes very slow. So climate sensitivity is not constant in time. So we have to keep that in mind as well.